Welcome, enthusiasts, to Bang with Science, where we don't just scratch the surface, we delve deep into the mysteries of the universe. With every episode, we embark on a journey to unravel the most profound enigmas of science. As we navigate through the mind-boggling concepts and theories, we aim to bring you closer to the core of our existence and the reality that surrounds us. In today's episode, we're about to dive into the fascinating and perplexing world of quantum physics and relativity. We're going to challenge the limits of your imagination and push the boundaries of what you thought was possible. So, buckle up and prepare for an exhilarating ride through the uncharted territories of science. Remember, in the realm of quantum and relativity, things are not always as they seem. Before we dive into the crux of our conversation, let's discuss the importance of quantum physics and relativity. These two areas of study have not only revolutionized our understanding of the universe, but also led to several technologies that are part and parcel of our daily lives. GPS, for instance, relies on relativity to provide accurate positioning, while quantum physics forms the basis of technologies like lasers and semiconductors. Now let's venture into the depths of one of the most fascinating realms of science. Imagine a world where particles can be in two places at once and cats can be both dead and alive at the same time. Welcome to the weird and wonderful world of quantum physics. In the early 20th century, a revolution was brewing in the realm of scientific thought. A few brilliant minds, including the likes of Niels Bohr and Werner Heisenberg, were about to turn our understanding of the physical world on its head. The rules of classical physics, which had stood unchallenged since the days of Newton, were suddenly not enough to explain the behavior of the tiniest constituents of the universe, atoms and subatomic particles. Enter quantum physics, a theory that describes a reality far removed from our everyday experiences. At its heart lies the principle of superposition, which postulates that a quantum system can exist in multiple states simultaneously. Yes, you heard it right. A particle can be in two places at once until it is observed. This leads us to the famous thought experiment of Schrödinger's cat, which illustrates the concept of superposition. The cat in the box is both alive and dead until someone opens the box to check. But the strangeness doesn't stop there. Quantum physics also introduces us to the concept of quantum entanglement. If two particles become entangled, a change in the state of one particle will instantaneously affect the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously dubbed it, has been experimentally confirmed, challenging our notions of space and time. So, as you can see, quantum physics throws our understanding of reality out of the window. It presents us with a world that is, in Bohr's own words, not only stranger than we think, but stranger than we can think. But hold on to your seats, because the journey into the depths of the physical universe is only just beginning. Now, let's shift gears and venture into the realm of the very large and the very fast with Albert Einstein's theory of relativity. During the early 20th century, a young physicist named Albert Einstein began to question the Newtonian mechanics that had dominated physics for over 2 centuries. This led him to formulate the theory of relativity, a groundbreaking perspective on how we perceive space and time. Einstein's theory of relativity actually consists of 2 parts. The special theory of relativity, proposed in 1905, which states that the laws of physics are the same for all non-accelerating observers, and the speed of light is the same for all observers, no matter their state of motion or of the source of light. Then, in 1916, Einstein introduced the general theory of relativity, which proposed a revolutionary concept. Gravity is not a force transmitted through space, but is a warping or a curvature of space-time itself caused by mass and energy. Let's break that down. Picture space-time as a flexible sheet. When a heavy object is placed on this sheet, it bends or warps the sheet. This is what Einstein suggested mass does to space-time. And this warping of space-time is what we perceive as gravity. Einstein's theory also gave rise to the concept of time dilation, the idea that time can speed up or slow down depending on how fast you're moving or how close you are to a gravitational field. The closer you are to a massive object, or the faster you're moving, the slower time passes for you compared to someone who is stationary or far from the gravitational field. This theory has been tested and proven in numerous experiments and has given us GPS, black holes, and the concept of the expanding universe. It paints a picture of a universe that's interconnected and flexible, where space and time are not absolute entities, but are relative to the observer. But here's the kicker. Einstein's relativity, as beautiful and as proven as it is, doesn't agree with quantum physics. It's like trying to fit a square peg in a round hole. So what's the deal? Well, quantum physics and relativity are both incredibly successful theories, but they don't play nice together. Why is that? Well, let's dig into this clash of theories. On one side, we have quantum physics, the theory that describes the tiny particles that make up our universe. On the other side, there's general relativity, a theory that describes gravity and the large-scale structure of the universe. Both theories have been remarkably successful in their respective realms. But when it comes to describing gravity at a quantum level, they're at odds. Here's the crux of the problem. Quantum physics suggests that forces, like gravity, are carried by particles. In the case of gravity, it's the hypothetical graviton. But general relativity describes gravity not as a force, but as a curvature of space-time caused by mass and energy. Now you might ask, why can't we just find a middle ground? Well, that's easier said than done. When scientists try to combine these two theories, they run into mathematical inconsistencies. These inconsistencies lead to infinities where there should be finite numbers, and that's a big no-no in physics. So why is it important to reconcile these theories? Because we want a theory of everything, a single framework that can explain all physical phenomena. But as long as quantum physics and general relativity remain incompatible, that goal remains elusive. You see, the universe doesn't care about our mathematical inconsistencies, it just does its thing. Black holes exist, quantum phenomena happen, but our understanding is incomplete. We know we're missing something, a key piece of the puzzle. So, where does this leave us? With a lot of work to do. Physicists worldwide are striving to solve this paradox. Some are looking for a quantum theory of gravity, others for new ways to interpret these theories. And who knows, maybe one day we'll find that missing piece and unlock a deeper understanding of the universe. It seems we have a paradox. Two theories, both correct, yet incompatible. This is one of the biggest unsolved mysteries in physics. So how do we reconcile these two theories? What's the missing piece of the puzzle? Let's dive into the ongoing quest for a theory of everything. This theory is the holy grail of physics, a single, all-encompassing, coherent theoretical framework that can explain and link together all physical aspects of the universe. Some physicists propose string theory as a potential solution. This theory replaces the point-like particles in particle physics with one-dimensional objects, or strings. It suggests that the different types of observed elementary particles are actually different modes of vibrations of the strings. Fascinating, isn't it? Then there's the theory of quantum gravity, another contender in this scientific race. It attempts to reconcile the realms of quantum physics and general relativity, focusing particularly on the elusive mystery of gravity, a force that quantum physics has yet to explain. However, finding a theory of everything is no simple task. Just imagine trying to find a single key that can unlock every door in the world. It's that complex. There's also the issue of empirical testing. These theories often involve phenomena that are currently beyond our ability to observe or measure. This is a significant hurdle, as theories are only as good as their testable predictions. Yet, the importance of this quest cannot be overstated. Discovering a theory of everything could revolutionize our understanding of the universe and the laws that govern it. It could lead to breakthroughs we can't even begin to imagine. But let's not forget that science is as much about the journey as it is about the destination. The quest for the theory of everything pushes scientists to explore, to question, and to innovate. It fuels the pursuit of knowledge and understanding, propelling us into a future filled with infinite possibilities. The theory of everything remains elusive, but the journey to find it is what propels science forward. The universe is a strange and wonderful place, and we're just beginning to scratch the surface of understanding it. Indeed, we've embarked on an epic journey today, traversing the intricate worlds of quantum physics and relativity. We've seen how these theories, born from the brilliant minds of scientists like Niels Bohr, Werner Heisenberg, and Albert Einstein, have shaped and continue to shape our understanding of the universe. Quantum physics, with its perplexing paradoxes, introduces us to a world where particles can exist in multiple places at once and can be entangled across vast distances. On the contrary, Einstein's theory of relativity paints a picture of a universe woven into a fabric of space-time, where gravity is the result of massive objects warping this fabric. However, these theories clash when we delve into the extremes of the universe, like black holes. Their differences highlight our incomplete understanding of the cosmos and fuel our quest for a single, all-encompassing theory of everything. Our journey today was not just about understanding these theories, but also about appreciating the spirit of curiosity and relentless pursuit of knowledge that drives scientific discovery. These theories, as complex and abstract as they may seem, are the results of that human curiosity, that insatiable desire to unravel the mysteries of the universe. So let's keep that spark of curiosity alive. Let's continue to question, to explore, to learn. Let's dive deeper into these fascinating topics. After all, every new discovery, every new understanding brings us one step closer to deciphering the grand cosmic puzzle. Remember, stay curious and keep exploring. Stay with Bang with Science and subscribe to Learn the Universe with Robiol and Sammy. Until next time.